Hello, everybody. I've posted PS11. It consists of 4 problems this week. I took 2 problems out that I've been planning to assign to you. I've left them in as PS11 5X and PS11 6X, which are just there in case you're interested in looking at those problems. One of them has to do with linear programming. The other was the caddis problem. So there'll be no caddis problem to do in PS11. The final exam will be coming out in about a week. It just depends on how fast I can create it and how fast Caddis can get it online. Just remember it'll consist of 3 Caddis problems, and you'll have 3 weeks to do them. Today's lecture comes again from 2018, and at the beginning of that lecture I was asked to answer a question about the narrow art gallery Caddis problem. So that's where we'll pick up, and then we'll move from there into the discussion of NP completeness.
Okay, so there's R. There is another parameter, which, what did I name that?
Unclosable.
Yeah, unclosable.
Unclosable room.
And K. All right. So what that's telling you is you've got an art gallery. R is a row number. Okay. So R is a row number. K is the number of rooms you have to close. Let's ignore unclosable for a moment.
Okay.
So what it's asking you to do is tell me if you just restrict this to being your art gallery, you ignore the previous rows. You just look at row R to the end. What's the maximum value you can get from these rows, these remaining rows, if you when you close K of them?
Oh, okay.
Okay, you're basically figuring out which K rooms to close so that you get the best result.
Okay, now it's starting to say. Thank
Okay.
you so much.
No, I'll continue. So if you didn't have to worry about, the thing is you can't close 2 rooms like that because there's no path to here. So if you didn't have to worry about that constraint, would this be a hard problem to solve?
No.
What would you do?
Just close all the lowest value.
Right, you just close the lowest value rooms, the K lowest value rooms. But the catch is that you've got to have a path through it. So this parameter here can be -1, 0, or 1. And this expresses a constraint on row R only. So if this parameter is -1, it means you can close either room. Okay? If it's 0, it's saying you cannot close this room. The only room you can consider closing is this one, and vice versa for 1. So that's what the parameters mean. Yeah.
I haven't even started parsing it yet, so if I go tell this, I'm sure I figure it out pretty quickly, but can you get multiple gallery instances on the input from Caddis? Like it said it will consist of multiple problem instances of galleries, but then on the examples there's only single instances of it. Does that make sense? Anyone?
Yeah, could someone help me with that, because I haven't looked at the actual.
Yeah, so he's asking, can you have one gallery, then terminated at a 0, 0, and then following right after that, another gallery terminated at 0, 0, and then so on?
You can.
In one run.
Right.
And can you?
I
Yes.
don't know. I don't
You
think
can?
I
Okay,
Yeah.
Anthony says yes.
Because the last row would be 0, 0, and then you start the problem all over again, and then 0, 0, and then you do it until you run out.
Yeah, it sounds like it's.
All right. Did anyone write the program without considering that and it passed anyway? Yeah?
Yeah.
All right. So it sounds like you don't need to worry about it. Whether it's allowed or not. No test cases that do that.
What happens if the number of rooms you have to close is greater than the number of rows?
Okay, so he's asking what if K is bigger than the number of rows left?
Joe.
Well, I never raised the test cases.
Yeah.
Well, it's a constraint that K is always less than N, so
Okay, so,
If you have more doors to close than rows left in your algorithm,
okay, so it won't be, it's not allowed in the end, basically.
But even if you have more, it would be 0 since you wouldn't be able to find a way through.
Right. You'd have to either close the entrance or close the exit. There'd be no way.
Okay. Okay. Any other questions? Okay, and let me just remind you again, do problem 2, don't submit it. Copy and paste you should be able to copy and paste your expressions from problem 2 into your Caddis program inside of sort of an if then else. And then you make sure your program works. Then you can submit 10-2. If you find a bug that you correct in your program, be sure you correct it in 10-2 before you submit. Okay, last time we were talking about, we're starting our exploration of NP completeness. And we talked about search problems. So my definition of a search problem here is that you're given an input to a problem, and you're asked to find a solution. Okay, that sounds pretty general. Furthermore, the extra requirement is that any proposed solution must be checkable in polynomial time. Okay? So there are problems that are so hard that even if someone presented you with a solution, you wouldn't be able to see if it determine if it was correct efficiently. Those wouldn't be search problems. We talked about the traveling salesman problem and wondered, can we classify it as a search problem? So here, we're given a weighted graph G, so that's the input. We're asked to find a Hamiltonian cycle of minimum total weight. Remember, Hamiltonian cycle is just a cycle that visits every vertex once and closes the loop. So it meets the first 2 criteria. You get a weighted graph. You're asked to find a Hamiltonian cycle minimum total weight, so there's an instance, and you're asked to find a solution. To call it a search problem, we would have to argue that there's an efficient way to verify that the solution is optimal. Okay, so if someone gave you a solution and claimed this is the optimal solution, is it? It's hard to see how you would verify it quickly. Okay. So let's leave that there. Let's recast it. The next thing we do is recast this problem into a slightly different form so that it was clear that it was a search problem. So this was our modification. You're given a weighted graph G and a budget B. So B is just an integer. And instead of being asked to find the Hamiltonian cycle with total weight at most B, finding the Hamiltonian cycle with the smallest weight, you're asked to find the Hamiltonian cycle whose weight is B or below. Okay? And then, is it easy to check whether or not the proposed solution is correct? Okay. How would you do the checking? Yeah?
check with every other individual and check with what it was conceived.
Okay, so you would check and make sure, first of all, so the solution would be a Hamiltonian cycle. So you'd have to check, okay, all the edges exist in the graph. All the vertices, the edges actually form a cycle. And the total weight of the edges adds up to less than or equal to B. And that's not hard to do. So it's, it's a little bit fuzzy whether we call traveling salesman problem a search problem, but clearly this is a search problem. Now that doesn't mean we can efficiently solve the Hamiltonian cycle problem. It just says that if someone proposes a solution, we can easily check it. So that's what makes it a search problem. Now, this is, I think, where we ended up. I told you the game we're playing now is we're just saying, we're dividing problems into, or algorithms or problems into 2 sets. There's the ones that require polynomial time, the ones that can be done in polynomial time, and the ones that can't. And we're considering the ones that can be done in polynomial time good, and exponential time is bad. And we spent some time talking about, why should any polynomial be considered good? And what was the bottom line? Why is it that polynomial time is, if someone discovers a polynomial time algorithm, it's exciting even if the polynomial is big? Yeah?
You can then improve on that polynomial. It was a breakthrough.
Right, so I use the word breakthrough. You're not going to, if there's some problem that no one had ever discovered how to solve quickly, and then someone comes up with a new algorithm that does, that solves it in polynomial time, that solver has come up with a new idea, has an insight that people didn't have before to make this possible. And that the insight, the thing's exciting. And using that insight, you'll probably be able to build on it, improve the algorithm further, solve other problems, and so forth. And in reality, no one comes up with an algorithm that's like that anyway. Or it's like that. It's 2 to the n, 3 to the n, n squared, n cubed, kinds of things we've seen before. All right, so that's where we stood at the end of class last time. Now, I've defined what a search problem is. What I'm going to refine a little bit, and I'm going to talk about 3 kinds of problems: decision, search, and optimization. And what I'm going to show you in the end is that the distinction between them really isn't that important. So first I'll make the distinction, then I'll sort of tear it down. So think of decision problems as being problems where the answer is a Boolean. Is there a solution? Here's a problem. Is there a solution? True or false? The answer is true or false. So that's a decision problem. Search problem. There we're asked, is there a solution? If so, what is it? And optimization problem, is there a solution? If so, what is the best one? Okay, so the traveling salesman problem is an optimization problem. The Hamiltonian cycle problem is a search problem, which you're trying to find a path. You don't have to make sure it's the best in any sense. What would be a decision problem that's related to traveling salesman problem and Hamiltonian cycle? Yeah?
Is this a Hamiltonian cycle?
Yeah. So the question here's a set of edges. Does it form a Hamiltonian cycle? Yes or no?
So instead of saying is there a solution, you shouldn't say is this a solution? Because if you say if there is a solution, it sounds like a search problem.
Yeah. Okay, I can buy that. So what he's saying is, I'm going to have a hard time fixing it, I think. I'll fix it later. He said I might have said that first line, is this a solution? Is this thing here a solution? Okay, so there's a traveling salesman problem. The decision version might be, well, no, I guess in this light, the word there makes more sense. Take the traveling salesman problem. The decision version might be, here's a graph and a budget. Is there a Hamiltonian cycle with total weight at must be? All right, you're not asking for the solution. You're just asking, is there one? Can this problem be solved? Perhaps that might be easier than actually finding a solution, is determining if there, just saying if there is one or not. Seems like that would be easier. The search problem would be, here's the graph and the budget. Give me a Hamiltonian cycle with total weight at most b, or tell me that there isn't such cycle. And the optimization problem that we've talked about. Give me this one with the smallest weight, or report that there is no cycle, that there are no cycles indeed. Okay, so a lot of problems, a lot of optimization problems come in search variance and decision variance, just like traveling salesman problem does. Okay, so decision, search, optimization. Okay. Now, what I'm going to show you now, yeah, I got a question.
Yeah, so how can you speculate about that a solution does exist without finding one? You stop me like a mathematical proof that you show that this could be solved, but like, how do you know it could be solved if you haven't found a solution, at least once?
All right, think about this problem. Suppose the problem is to factor large numbers. Okay, so the decision version would be, let's suppose that the search problem is you're supposed to find all the prime factors. Okay, n is the number. Find all the prime factors less than n, or report that there are no factors, no prime factors less than n. Okay, what would the decision version be? Yeah.
Are there any factors, like, is it possible for there to be a factor?
Right, the decision version might be, does this number have any prime factors less than n? So that question then is, essentially, the decision version is, you're asking, is this number prime? And you can tell if a number is prime without factoring it. But having said that, what I'm going to show you now is that if you can solve the decision problem quickly, and by quickly, what do I mean? Polynomial time. So if you can solve the decision problem efficiently, you can solve the search problem efficiently. Okay? So, suppose we have search, decision, and optimization variants of the same problem. Okay? And so let's assume we have a decision algorithm that runs in polynomial time that'll tell you whether or not a Hamiltonian cycle exists. Let's use it to create an algorithm that'll find a Hamiltonian cycle. Okay? So let me rephrase that. We've got an algorithm over here. You can give it a graph and a budget, and it will report yes or no. There is a Hamiltonian cycle with total weight less than or equal to b. So let's say we got that written. And let's postulate it runs in polynomial time. If we got that, we can come over here and write a polynomial time algorithm for the search version to actually find the Hamiltonian cycle that the decision version claims exists. And we can do it without modifying the decision version. We're going to use the decision version. We're not going to modify it. Okay? Can you think of how we could do that? And furthermore, the search version we come up with is going to run in polynomial time. So how can we trick the decision version into giving up the answer, even though it doesn't really have the answer? Yeah?
Just like recording its progress and moving through.
Well, you say recording is progress. No, we're not going to look at it internally at all. It's a black box. All we can do is feed it a graph and a budget, and it will tell us yes or no. And somehow we want to use that black box to obtain a solution to the search.
Give it all of the possible Hamiltonian cycles and then say, is this, or,
Well,
no, that doesn't work. So.
yeah, that won't work, because it could be an exponential number, yeah?
So you start off with, is there a budget of 0, then you double it, and is there a budget of 1, 2, 4, and then once you see that there is, then you start narrowing it down using bisection.
Well, yes, but that'll tell us what the minimum budget is for which there's a solution, but it's not going to tell us what the solution is. We've got to find the solution. You were going to say something?
Would you like you removing voices?
Okay, that's it. We're going to do surgery on the graph. We're going to modify the graph that we give to the decision algorithm. So let me show you what we're going to do. First, we're going to run the decision algorithm and check to see if there's a solution. Okay? If there is no solution, we just stop. Right? There's no chance, there's no point in trying to find a solution if it doesn't exist. Otherwise, we're going to do the following for each edge in the graph. We're going to take the edge out, and then we're going to ask, does this modified graph have a solution? Now, what if the answer is yes?
And that must be in the solution.
Then that edge is part of a solution, and we better put it back in the graph. But if the answer is no,
Just leave it out.
we leave it out because it doesn't seem important. If we keep doing this, in the end, the only edges left will form a Hamiltonian cycle with total weight at least b, at most b. Okay? So let's just look at this in pictures. So there's our graph. We've seen it before. We know there's a solution. So we're going to take the edge from A to B, and we're going to take it out. And now we're going to take this modified graph, we're going to hand it to our decision algorithm. We're going to ask, does this graph here have a Hamiltonian cycle of weight 16 or less? Okay? It turns out it doesn't. Hard to convince you of it, but I stared at it. It doesn't have a solution. Yeah?
I'll ask after.
Okay. Hopefully you're not going to tell me there is a solution. Okay? All right. So that graph doesn't have a Hamiltonian cycle, but the original one did. So that edge right there, that between A to B, must be part of at least a solution. So we'll stick it back in. All right. What were you going to ask?
So what if there's multiple solutions? Wouldn't you return a single solution, you return.
Well, it turns out if there's multiple solutions, and there's some edge that's part of one solution and not part of the other.
Yeah.
Okay, when we take it out, it'll say, yeah, there's still a solution. So we've essentially eliminated one of the duplicate ones by not putting it back in. Yeah. So what do we do next that we put this edge back in?
Pull up.
We're going to take this edge here. We're going to take it out. We're going to ask the decision algorithm, okay, here's a graph, here's a budget. Does that have a solution? It says yes. Turns out, in fact, that's it. Now, it's not going to tell us that's it. It's just going to say, yes, there's a graph, but I'm just showing you that's it. So, we're just going to leave it out. It doesn't, that edge isn't important to the solution. This graph has a solution that's also a solution for the original graph. So, we'll look at the edge from C to D. Take it out. We find out it's crucial. So, we put it back in. And we just keep doing that. So, there's that edge. Take it out. Ask, is there a solution? The answer is yes, so we leave it out. We consider, well, that's the solution. Okay? Then we're going to take that one out. Yeah?
Could you have left 3 in because F could have cut across this E? Or
Left which edge in?
3? Or sorry, the top right one, the third one you did? Or
That one there?
never mind.
It's
We're good. Decide.
From B to B? Okay. Okay, so we tested that edge. We find out, no, there's not even a Hamiltonian, there's no cycle at all if we take that edge out, so we better put it back. We consider that edge, that one turns out to be crucial. That edge turns out not to be crucial. And so on. That edge is not important. We leave it out. That edge is crucial. That edge is crucial. This edge doesn't matter. So if we did this for every edge, in the end, all we're left with are the edges that form a Hamiltonian cycle of total weight 16 or less. Now, if we can solve the decision problem, if every call to the decision problem runs in polynomial time, what can you say about the complexity of this search algorithm? Yeah?
It's also polynomial time
Okay, it's also polynomial time. Why?
because it's just E calls to a polynomial
Right.
time algorithm.
So the complexity is E times the cost of the decision algorithm. So that means if the decision problem can be solved efficiently, then the search problem can be solved efficiently. That doesn't mean that if the decision problem can be solved in some polynomial time, say solved in n squared time or e squared time, that the search problem can be solved in e squared time. It would require e cubed time. So we're not going to get as good an algorithm. But if the decision algorithm is polynomial, our search algorithm is polynomial. And that's all we care about now. We've got a good decision algorithm, we've got a good search algorithm. Okay? Any questions I could answer about this? You can play this game on a lot of algorithms. And there'll be, on the next assignment, you'll be doing a thing like this where you're going to show how to solve a certain problem given a decision algorithm. Okay? All right, now, let's play the same game and show you how to, assume you have an efficient search algorithm, show how to turn that into an efficient optimization algorithm. Okay? And the problem we'll pick is, again, we'll stay in the traveling salesman example. So our decision problem is going to be, our search problem is going to be, here's a graph and a budget, give me back a solution that's within the budget. And the optimization will be TSP. Here's a graph, give me the, forget about the budget, just give me the best answer. All right, how can we do that kind of thing? Yeah?
Start with some maximum budget and then just keep moving it down until you hit there is no solution.
Okay, so he said start with some maximum budget. So what would be sort of an upper bound on the total weight of a Hamiltonian cycle in a graph? How could you quickly come up? Yeah?
Then some of the weights of the maximum spanning tree.
Okay. He said the sum of the weights of the maximum spanning tree, but you say something even simpler. Yeah.
Just the sum of all the weights in the graph.
Certainly, if you add up all the weights and all the edges, the best cycle can't be less than that. Can't be more than that. Or if you sum up if you find the V edges with the highest weight and add those up, That'll be an upper bound. So it's not hard to come up with an upper bound, did you?
Yeah.
Right? And so then the suggestion is, so let's say that we've got a graph with 100 vertices and a whole bunch of edges. And so we take either all the edge weights and add them together, that gives us an upper bound on the eventual answer. Or we take the V heaviest edges and add them together, that's an upper bound. So let's say it adds up to 1 million. So we could say, okay, we ask the search algorithm, give me a solution with total weight 1 million, with 1 million or less. And what if it says no? Can't. Right? If it says no, there's no solution, then there can't be a solution to the traveling salesman problem. What if it says, yes, there is such a solution? Okay? So Anthony said go to 500,000. You said cut it by 1.
Yeah.
Let's take that. Suppose now we cut it down to 999,999 and say, is there a solution? And it says yes. So we keep cutting it by 1 until the answer is no. Suppose we get down to like 112,000 and it says, no, there's not a solution. Right? So we know that the optimal solution is the one that was the one before it. That makes sense? You just keep cutting it by 1, cutting it by 1, cutting it by 1, cutting it by 1 until the answer becomes no. You back up to the previous question you asked, and that's got to be the best. But what's the problem with that? It requires exponential time. We end up doing an exponential number of, remember the size of the problem, the pertinent size of the problem in this case is the size of B. And we could have a 30-bit B that requires 1 billion method calls. So it's a 2 to the log B algorithm. So that's no good. Because yes, it would solve the problem, but it would require exponential time. We need to be able to do this in polynomial time. So that gives us Anthony's suggestion, which is basically do a binary search. So you ask, is there a solution for 1 million? And if it says yes, you say, okay, is there a solution for 500,000? It says yes. You ask, is there a solution for 250,000? It says no. So now you know the answer between 500,000 and 250,000. So you just do a binary search in those bounds until you find the smallest number for which the answer is yes. Okay? So that only takes log budget calls. Okay? All right, so that's basically what we said, except here I do a min and a max. I find out the smallest it could possibly be, the largest it could possibly be, and do a binary search in there. Each probe of the binary search involves calling the search algorithm. But we'll find the answer that way. Yeah?
Would it be possible to do a search without a weight and then use whatever that is as the max?
You mean find a Hamiltonian cycle?
Yeah.
Okay. Yes, but we don't know that you're postulating there is a way to find a Hamiltonian cycle that's efficient. All we know is that we're assuming there's a way to efficiently solve the Hamiltonian cycle problem.
Right.
So essentially, making an absurdly large budget
Yeah.
and then using that search problem is the same as asking, is there a Hamiltonian cycle?
Right.
So
I guess I was just saying, like, try to minimize how much searching you're doing by finding a cycle first and then just using that as your maximum.
yeah, but finding a cycle is
Okay.
basically what we're doing by calling the search problem. Now, the reason I've done this exercise is not because this is a necessarily practical way to solve problems. It's because I don't want us to have to stress about whether we're talking about decision problems or search problems or optimization problems. Because you can take most any problem, any optimization problem, and cast it in one of these forms. What we've just shown is that, if you can solve one in polynomial time, you can solve the other version in polynomial time. So we won't worry about, we're pretty much concentrated on search problems from here on out. But anything we discover about search problems will apply to decision problems, will apply to optimization problems, because we can convert one to the other. Yeah?
So when we already verify that the decision problem will be polynomial problem, so does that make sure that the search problem would just be also polynomial?
Well, yeah, so what it means is that if we could find a polynomial time algorithm that solves the decision version of traveling salesman problem, we would then have a polynomial time algorithm for the traveling salesman problem. So in that sense, they're equally hard. If you could solve decision or search, you would have the optimization problem solved. Yeah?
Is there any reason why either of those steps hasn't been solved in a faster time than polynomial? Is there
Faster than polynomial? Well, they haven't even been solved in polynomial time. Right? So I said, you know, if there's a polynomial time solution to the decision version, there's a polynomial time solution to the TSP version. But no one's found such an algorithm for any of these. No one knows a polynomial time algorithm for any variant. Okay? The best known solutions are exponential time. Okay? And it's considered unlikely that a faster algorithm will be solved, will be found. And that's in fact what I'm trying to explain is why that statement I just made is true, but we're not quite there yet. Okay? So for now, what we've done is shown decision search optimization. Distinction really isn't important. Okay, so let's F5 do that for me. Thanks. Okay, this is sort of the next set of slides, but what's at the top just repeats what we said already. This is the definition of a search problem. Let's look at some examples of problems. So think about searching. So for every one of these problems, we want to show that it's a search problem. And so what we have to say is every search problem has an input, an instance. And so imagine this problem where the input is an array of integers a and an integer x. Okay? And the question is, does this integer appear in the array? Okay? So a solution, a solution would be an index I such that a sub I is x. Is that easy to verify? Yeah. You just look in the array of index I and see if an x is there. So if someone says x appears in index I of this array, you easily check it. That's a search problem. It's easily checkable. What about factoring? So the instance there might be an integer n, and the solution is an array of prime factors. Okay? That's easy to check. We just check that each number is prime, and we multiply them all together and see if we get n back. That's a search problem. So the key step is that there's an efficient way to check that the answer is correct. Okay? So let's look at a different problem. Independent set problem. This is given an undirected graph G, find the largest set S of vertices such that, this is a little hard to, I don't even have a picture for it. I had this, we didn't discuss this problem earlier. Basically, you've got a graph G, and you're supposed to imagine you've got a bunch of edges between them. Now, I've got to draw on the board here. I've lost my stylus. So. I've got to find my marker. Lost it too. There it is. Okay, imagine you have a graph G. And you want to find the largest set of vertices here, such that no two vertices in the set have an edge between them. So what would be, that's the optimization version. The search version would be, how did I put it? No, that's the optimization version up there. What would be the largest set of vertices here? Let me give these some letters so you can talk to me. So he suggests C, B, F. So the no edges between them, that's 3. Could we do 4? I don't believe so. A, D, F. Okay?
No.
Yeah, ADF doesn't even work. Okay. So that's the question. That's the optimization version. What would be the search version of this problem? Yeah?
Is this set independent set?
That would be the decision version. Decision version would be given a graph. Well, decision version would be given a graph. Does it have an independent set of size at least 3? What would the search version be?
What is this?
Given a graph and a number n, give me back a independent set of size at most n. Okay, so the question is that easy to verify? So suppose when someone gave you back the set, n was 3 and someone gave you back the set B, C, F. Could you verify that that was actually an independent set of size at least 3? At least 3, I should say.
Yeah.
Yeah, you just make sure these are all vertices, there are no edges between any pair,
There's 3 of them.
and that there are 3 of them. Yeah. So that's a search problem, but the search variant is a search problem. Okay, let's look at another one here. Satisfiability problem.
That's the general.
So you're given a Boolean formula in conjunctive normal form. So conjunctive normal form means pluses or ors. So this means x or y or z. X or y are Boolean variables, so they can be true or false. X or y or z, this is x or not y. This is y or not z, and so on. And then they're anded together. So it's this, and this, and this, and this, and that. Okay? Hugely important problem that comes up in program verification. The satisfiability problem is to find a way to make those, come up with an assignment of true and false to the variables that makes the whole expression true. Okay? So, is there an assignment here? Yeah?
So x equals true, y equals false.
Okay, x equals true makes this one true, and it makes that one true.
Y
And
equals false and z equals false.
so you're making z false, that makes that true, this whole thing true. This one is true, and you made y false, so it makes that one true. So actually, there are lots of solutions to that. There's mine. Y doesn't really matter. What's important is x is true and z is false. Okay? Is that a search problem? Namely, can it be verified efficiently? What will be the verification?
Evaluate it.
Right, you just plug in for x, y, and z and evaluate it and see if it's true. That's easy to verify. But no one knows an efficient way to solve the problem.
What's it?
What's that?
Decision one, isn't it? If you give me x, y, z, is it the answer? That's a...
Well, the search variant would be, here's the thing, give me a solution. The decision version would be, is there a solution? Is there a way to do it? Okay? So, independent set problem, easy to verify. No one has ever discovered an efficient way to solve it in general. The best known algorithm is exponential. Satisfiability, same deal. Easy to verify an answer. No one's ever found an efficient solution. Now, I'm going to tell you two variants of this. 3-sat occurs when there are no more than 3 literals per clause. So this is a 3-sat formula. There's no more than 3 in each of these things. 2-sat's when there's no more than 2 literals. 2-sat has an efficient solution. 3-sat doesn't, oddly enough. On the other hand, 3-sat, you can take any statement of logic that uses ands and ors and nots and turn it into 3-sat. The same is not true of 2-sat. So 3-sat's fully general, 2-sat isn't. Okay.
Yeah, you can map 4-sat to 3-sat.
Yeah. You can map any sat to 3-sat. Right. Any higher or anything. Forget about the 3. The thing. You take any Boolean expression, you can turn it into 3 set. Okay, this is the Hamiltonian path problem. Your book calls it the Rudrata path problem. So, but that's the only place I've ever seen it called the Rudrata path problem.
Wasn't that like the Knight's Walk is Rudrata's and Hamiltonian was the one that's more general?
They're synonyms as far as I'm concerned. So, that's what we've seen before. Given a graph G, find a path that visits every vertex exactly once. Okay, that's what we've been talking about. So, that's a search problem, easy to verify. We already spent time talking about that. There's a solution, except I left one. Oh. This is,
Path, not cycle.
yeah, we've been talking about the Hamiltonian cycle problem. The Hamiltonian path problem is related. But the Hamiltonian path problem is, you start somewhere, you visit every vertex, but you don't go back to the start. You don't have to go back to the start. So even if you took, say, this edge out right here, you'd still have a path. You may not have a cycle, but you'd have a path. Okay? Hard to solve, no one's found an efficient way to solve it, easy to verify. Traveling salesman problem, okay, we talked about that. Easy to solve, hard to solve, can be verified. Yes?
So when you say that, can't you consider the verification process the solution process as well? That is the way to solve it. Why are they?
Well, how do you know? So he's asking, would the verification process give you a way to solve it? Okay, well, how would that be?
Well, it's like you talked about. First, you get the different steps, and you black box it, and keep removing parts, and you construct the solution after going through that whole process.
Okay, so let's take the factoring problem. So to verify that two numbers are factors of a third, you just multiply them together. Right? Factoring is pretty difficult. Multiplication is pretty easy. So how would you take multiplication algorithm and use it to factor? So basically, yeah. It is not. Sadly, it is not possible to take take a verification algorithm and turn it into something that's solved. But that shouldn't be that surprising. There's a big difference between being given a proposed solution and checking it's correct and finding the solution in the first place. Yeah?
So if it can be verified in polynomial time, does that indicate that you can solve it in exponential time? Because you could just take every possible permutation and then just verify, is this a solution?
Yeah, you have to assume that there's only an exponential number of possibilities.
Okay.
Yes, if you can try all the possibilities, and essentially that's how most of these problems are solved in exponential time. Is you try all the possibilities and try to verify them. Yeah.
For the previous one, you said TSP could be checked in polynomial, or was it TSP as a search problem?
Well, TSP, the search variant of TSP, can be checked in polynomial. And I showed you how to take.
Oh, for given weight, not the minimum weight. So it's not.
But then I showed you how to reduce the optimization version to the checking to the search problem. Okay. Euler path problem. So for this one, we want to find a path that traverses every edge exactly once. So it's sort of like a dual to the Hamiltonian path problem. There we want to visit every vertex once. Here we want to visit every edge once. This one can be solved efficiently. There's a simple way to solve this problem. So it's not clear. I mean, why should this be an easy problem to solve and the Hamiltonian path problem harder? But they are. Sometimes it's confounding. Things that seem like they're sort of the same, ought to be similar difficulties on. Knapsack problem. We talked about that. You can think of that as a search problem. There's an optimization problem. You think there's a search variant. Subset sum problem. You're given a set of numbers and an M, a goal. You're supposed to find a subset of S that sums to M. So what is a subset of S that sums to M?
Eight, 2, 9, 1.
2, 3, 1, 14.
2, 3, 1, 14. Yeah, the various ones. Turns out There is no known efficient solution to that problem. It's easy to verify a solution. Someone gives you a solution, you just make sure it's a subset of S. You make sure it adds up to M. But actually finding the subset, no one knows how to do it efficiently. The shortest path problem.
Distress?
Given the weighted graph G, find the shortest path from U to V that doesn't use any edge more than once. No one's ever solved it. You throw in the restriction that there is no cycle of net negative cost. It can be solved efficiently, but in the general form, without that restriction, no one has found an efficient solution. Yeah?
So when you say no one has found a solution, do you mean that it hasn't been discovered yet, or it was mathematically proved that there is no better
No.
solution?
Okay, so he's asking an important question. When I say that no one has found an efficient solution, what I'm not saying that, it's also the case no one has proven that there is not an efficient solution. So either there is no solution or there is one and hasn't been found yet. We don't know which. But it's considered very unlikely for reasons we're going to talk about eventually. It's considered very unlikely there is an efficient solution. Yeah?
What's the difference between shortest path problem and something that Dijkstra's would solve? Because Dijkstra's is polynomial, right?
Right. But for Dijkstra's, we said no negative edges. For Bellman-Ford, we said no cycles of negative cost. This isn't saying anything about negativity. It just says find the shortest path that doesn't use any edge limits. Okay? So the shortest path that doesn't involve a cycle.
So you could have a crazy path that tries to hit all the negative edges.
Yeah. So the general shortest path problem, no one's found an efficient solution. You put a little extra restriction on it, there is an efficient solution. Okay? So these are just examples of problems. And your book has examples of famous problems. So here's a chart. On the left are problems, or on the right are problems known to be easy. So how do we know they're easy? Yeah?
Because it can be solved with polynomial time.
Right, because someone found a polynomial time algorithm for them. So 2 sets easy. Someone found an algorithm to solve it to fit quickly. Minimum spanning tree is easy. You solve that. Shortest path from the no negative cycles. We solved that. Independent set on trees. The independent set was I was talking about over there. Turns out if your graph is a tree, the independent set problem on trees can be solved efficiently. The Euler path problem can be solved easily. On this side are problems believed to be hard. So for example, 3 set. Okay, 2 set's easy. 3 set, no one has ever found an efficient solution. Maybe there is one. We don't think so. Traveling salesman problem, hard. Why did I put it on the same line as minimum spanning tree? 3 set and 2 set, it's clear to see there's a correspondence. Yeah?
There's the same correspondence between traveling salesman problem and minimum spanning tree as there is between independent set on graphs and independent set on trees. The minimum spanning tree never has any cycles, like nothing that leads back.
Okay. So, yeah, all right. So the way I think about it is both those problems involve hooking up all the vertices in some way. So for traveling salesman, you're trying to find the cheapest way to hook them all up in a cycle. For minimum spanning tree, you're trying to find the cheapest way to hook them all up in a tree. Well, it's not obvious. If I just told you those 2 problems at the beginning of the semester, I don't think you would say, clearly the traveling salesman problem is much harder than the minimum spanning tree problem, but it appears to be. Shortest path with no negative cycles, they said was fast. General shortest path, we don't know, but no one's ever solved it. Independent set on trees, easy. Independent set on graphs, apparently very hard. The Euler path problem, where we're visiting all the edges, easy. The Hamiltonian path problem, we're visiting all the vertices, hard. Knapsack problem,
There's not an equivalent easy one.
hard. I don't know what to put as the equivalent. Now you may think that we have solved the knapsack problem, but yes, we use dynamic programming, but it turns out that the solution requires exponential time. And to show you that, imagine, I think I mentioned this at the time, imagine you have a small table and a huge, huge, huge knapsack. going to take, so the dynamic programming solution has got to fill out a massive cache. Imagine if your knapsack could hold 1 billion elements. So now you've got to, so 1 billion is just a 30-bit number, but you've got to fill out a 2 to the 30-bit table. So it's even the dynamic programming version requires exponential time. Subset sum problem, which I showed you, exponential time, or is believed to require exponential time. So this is the perplexing thing. In the early days of computer science, people were solving problems left and right, but we kept running in, I should say we, but computer scientists kept running into these problems which they wanted to solve, but no one seemed to be able to make any progress on them. And it wasn't until about 1970 that this was discovered. It was discovered that what these problems all have in common, these turns out to be what are called NP-complete problems. If any one of them can be shown to require exponential time, that means they all do. So they're equivalent in that form. If any of them can be solved efficiently, they all can. So either all these can be solved efficiently, or none of them can. It's not the case that we're going to find an efficient algorithm for subset sum, and we're going to prove that the Hamiltonian path problem requires exponential time. They're either all exponential, all require exponential time, or they all can be done in polynomial time. Now, I haven't proved that yet. That's where we're headed. What side would you bet on? How would you show that they require they can be solved in polynomial time? What's that involve?
You come up with an algorithm.
Right. You just come up with an algorithm for one of them. All right. So it is telling that how many programmers there are in the world. That if you would think that if there was a fast way to solve one of these, someone would have stumbled on this at some point. Thousands and thousands of NP-complete problems. No one has ever found an efficient solution to any of them, despite armies of people trying. Okay? How would you prove that one of them requires exponential time? Yeah?
So we build a sort of like decision tree like we did at the beginning.
Yeah, it would be a proof like that decision tree, much more complicated, that decision tree proof for sorting. But basically, it takes a highly trained theoretical computer scientist, applied mathematician, to work on that problem. It would be a mathematical proof that some problem requires exponential time. So that's a smaller set of people that can work on the problem. So, for those reasons, the smart money says that we're not going to find an efficient solution to any of these problems. Okay? We're sort of getting ahead of myself. Well, I'll show you why these two things are facts eventually. Let's take a break. All right, let's get started again. Okay, so I just want to make sure that you internalize this idea that we're going to be discussing the difference between problems known to be easy and problems believed to be hard. And to do that, I'm going to define two sets. First set is NP. NP stands for the set of all search problems. So that's basically the case where solutions can be verified in polynomial time. And then the set P, well, I guess I'll talk about it a little more here. So by verification algorithm, I mean you take a problem instance, say a graph, and you're taking a proposed solution, let's say a set of edges. The verification algorithm will output true or false. Is the proposed solution actually a solution to the problem? Okay, so the verification algorithm takes both those pieces in and outputs true or false. So that's the set NP. The other property is that V has to run in polynomial time. The verification algorithm has to be a polynomial time algorithm. And I don't know why I said C right here. It should be V. It says V right there. Okay? then P is going to be the set of all search problems that can be solved in polynomial time. Okay? So you feed in a problem instance, you get out the solution, and the algorithm A runs in polynomial time. Okay? So we spent all semester looking at problems like this. You feed in a problem instance, you get out a solution in polynomial time. All right, let's widen our scope. Let's consider problems. Now we're considering problems that can be checked in polynomial time, verified in polynomial time. So if we go back to the previous slide, every problem on here is a member of NP, because they can all be checked in polynomial time. The ones on the right are part of the set P. The question is, are these also part of P or are they not? So those are our two sets. NP is the ones that can be verified in polynomial time. P are the ones that can actually be solved in polynomial time. Now, it's clear what P stands for, polynomial time. What does NP stand for?
Non-deterministic polynomial time?
Yeah, it turns out NP stands for non-deterministic polynomial time. Most students would look at this and think something different. What's a more not polynomial time? Okay, non-deterministic polynomial time. In the 70s, so the theory of incompleteness states in 1970, and in its original form, the definition of NP didn't talk about checking in polynomial time. It talked about solving it on a non-deterministic computer in polynomial time. And so that definition is not used so much anymore because it requires defining what a non-deterministic computer is and what it means to solve in polynomial time on a non-deterministic computer. Essentially, it means trying all the possibilities at the same time in parallel and finding one that works, which is equivalent to being able to verify something quickly. So non-deterministic polynomial time is kind of an anachronism. That's what it means. That's what the letters mean. Acronym means. And here's the million-dollar question. What's the relationship between P and NP? So one possibility is that P is a proper subset of NP. So think of that as a particular problem. Okay? This would be a problem. So if this is the way the world is organized, then that would be the problem. This would be some problem on the right-hand side of that table I gave you. And this would be one of those problems like traveling Salesman problem on the left-hand side. So P is a proper subset of NP. That's one possibility. There are some problems that can be verified in polynomial time that cannot be solved in polynomial time. Okay? Another possibility is P and NP are the same. Okay? That they're not, that any problem that can be verified in polynomial time can be solved in polynomial time. And it is not known which is the case. Does P equal NP or does it not? Most people think that's the case. P is not equal to NP. There are some problems that can be verified quickly that can't be solved quickly. It may be that we wake up tomorrow and someone has proven that P equals NP. Now, what do you think that proof would look like? It would just be someone finds an algorithm for the traveling Salesman problem, say. A fast algorithm. Bam. Game over. P equals NP. That would be stunning. Folks are all the time publishing proofs, mathematical proofs, that P does not equal NP. Okay? They're always wrong. Most, you go on the internet, you can find lots of proofs that P equals NP. Most of them are by, undereducated hobbyists, essentially, cranks. There have been serious proofs. There was a proof a few years ago that P equals NP by someone with bona fide credentials in the field, and it survived scrutiny for a few days. So there was a period of a few days where there was this thought that maybe it had been proven that P is not equal to NP. But in the end, that proof had a bug in it.
Other than, when proving it, is there any evidence towards one or the other? Or...
Yeah, there's lots of evidence. It's hard for me to characterize it. One interesting thing is that, so take factoring, the factoring problem. Where does it lie? Is it a search problem? Given a number, find its factors? Yeah, so it's a search problem. It's easy to verify. All right, someone gives you, say, the prime factorization of a number. It's easy to verify that that is a prime factorization. We've already argued that. So it's certainly a member of NP. Okay? No one has found an efficient algorithm to factor it. So suppose, but no, it's not proven to be NP complete. So it has this funny status. It's not known to be NP complete, but there's no known efficient algorithm for it. So suppose P was not equal to NP. Where most likely would factoring lie? Well, we don't know. Maybe it would lie, maybe it would be a problem of type 2, a problem of type 1. It just depends. We don't know. But what if P equaled NP?
Then it's definitely
If P equals NP, factoring is going to be inside that circle. It's a problem from NP. If someone tomorrow proved that P equals NP, that would imply factoring can be solved efficiently, and e-commerce, as it exists, would be doomed. So we hope P doesn't equal NP for that. Another thing is, take quantum computers. There are quantum algorithms to do factoring efficiently, but no one has ever discovered a quantum algorithm for an NP complete problem. So that's a bit of, something. Yeah, there's nowadays, in the 20th century, mathematicians turned from proving things. Before the game was proving theorems. In the 20th century, there was a lot of activity of proving that there were things that couldn't be proven one way or the other. So computer scientists are sort of nibbling at NP completeness that way by considering, well, maybe it's impossible to prove either way, or they will prove that certain techniques for proving NP completeness won't work. So there's a lot more. Yeah.
So isn't the problem of P equals or not equals NP also P equals NP problem or NP problem? So if you can come up with like a million or a non-deterministic number of algorithms, you feed them through and you check them, and then you check whether or not the algorithm actually.
Well, okay, that's a good point. So think about the problem of proving a mathematical theorem. Okay? You can think of what's formally a mathematical theorem like as some sequence of statements that leads from the beginning to the conclusion. So one way you could prove a theorem is by just start generating all possible sequences of mathematical statements and checking. So you can think of proving a theorem as a search problem. Is it efficiently checkable? If someone gives you a proof, a formal proof, can you check that it's correct? Yes. Yeah. You just go step, 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 see if it works. So the problem of proving a theorem is a member of NP. So if P equals NP,
we can check all.
then there's an efficient way to generate machine proofs for any theorem. So mathematicians would prefer that P be not equal to NP. Then they'd be out of the job. Okay? Yeah.
So does that make it like an order of magnitude less likely that P equals NP because mathematicians have been working for thousands and thousands of years and they've never found an efficient way to just generate proofs algorithmically?
30 years?
Well, it's computer scientists that would be generating proofs.
But
yeah,
well, I mean
that's just more.
Because mathematics is like,
Yeah, we think mathematics is hard,
yeah,
and at P equals NP, mathematics is easy,
right,
in some sense.
or could be made easy via some algorithm.
So like making a symphony is like the same as hard as the
Right.
same.
Think about. I have a slide later on that has this very example, but just think of the problem of writing a beautiful music. Okay. If you think of that as a search problem, then it's easy to generate music. Is it easy to tell? If you could come up with a way of saying whether or not a piece of music was beautiful, and P equals NP, then you have an efficient way to generate beautiful music.
Yeah.
Okay? So anyway,
Not likely.
we haven't even defined formally what it means to be NP complete, so we're getting ahead of myself, but it would have all kinds of repercussions. All right, this is what we've just been saying. If P equals NP, then all these problems we think are hard are easy. If P is not equal to NP, it means that all these problems that we think are hard really do require exponential time. So that's the most likely outcome most people think. Now we're going to get into talking about what the definition of NP completeness is. We've got to work up. And to do that, I've got to introduce the notion of a reduction. For some reason, when I put this diagram up, people decide right away that it's just too hard to understand and they don't try. Okay? It's not. Right? Don't come up with this preconceived notion that a reduction is some mysterious thing. But here's the thing. Suppose we have some problem we want to solve, problem A. And so that dotted line is supposed to represent, the inside there is we want to put an algorithm that can solve problem A. And it will take some input, and the output will either be a solution or the report that there is no solution. So maybe we're trying to find an algorithm for A where A is the Hamiltonian path problem. So we input a graph, and out comes either a path or you're told there is no path. There's no Hamiltonian path. Okay? So what does the word reduction imply? Yeah?
You're just showing that this algorithm is just a special case of another algorithm?
Well, he said we're showing one algorithm as a special case of another. That's what you do with a reduction. What do you do when you have a problem you want to solve, and there's one sort of like it in the library? Right? It doesn't take quite the same inputs as the original. It doesn't produce, that's a problem you want to solve. And it doesn't produce quite the same outputs, but it's similar. What do you do? Yeah.
So you kind of apply the known subproblem to the new problem. And
Yeah,
then
so you take your problem and you modify it somewhat so it can be solved by the existing library function, and then the output isn't quite the form you need, so you massage the output. Okay? You do that all the time. You want to solve a problem, you've got some pieces that exist, and you've got to write some code in order to use the pieces, right? You've got to, you could argue that's what programming is. It's just doing reductions. It's taking some problem you want to solve and turning it into a problem that you can solve with the tools that you know. Okay, so what we're going to do is we're inside that box, we're going to put the algorithm for A. And the key component is going to be an algorithm for some other problem B. So we're going to assume that there's some problem B that we can solve. And what we're going to do is we're going to take the instance when it comes in and we're going to modify it. So we're going to have some program F that takes I and turns it into F of I. So it takes input designed for A and turns it into input designed for B. And then if B produces a solution, we're going to convert it. There's going to be some program H that takes the solution produced by B and turns it into a solution for A. And if B reports there is no solution, we're going to report there is no solution. So what we got to put in the box is an algorithm for B, F, which does the conversion going in, and H, which does the conversion going out. Yeah.
So could you think of F as just an adapter of the input of A?
Right. F is an adapter of the input of B. I mean, maybe you're trying to solve the problem, find the largest element in the set, okay? Find the largest element in the array, and B sorts the array, right? So you might do something like you take the array, you sort it, and then you take the largest element out. So what would be F in that case? So A is a sorting algorithm. You're trying to find the largest element. What would F do to the array? Yeah, it would do nothing. F wouldn't have to do anything. So you take the array you're trying to find the largest element to, and then you would feed it unmodified to B. B sorts it. What would H do?
Pull the last
It would just pull the last element out and report that as the largest. And then in this case, there would be no case where, well, if the array is empty. If the array is empty, you'd have to report there's no solution. I mean, that'd be a tortured way to find the largest element, but that's the idea. You've got some algorithm you want to use, so you've got to dance a little bit to make it work. That's called a reduction from problem A to problem B. So let's let A be the problem of finding a Hamiltonian path between two vertices in a graph. Suppose you want to find a Hamiltonian path. That means not a cycle, There's a Hamiltonian path between two vertices if you can start at one spot and end up at the other, end up at another vertex. You visit every vertex once and end up somewhere else. You don't have to close the cycle. So let A be that problem. Let B be the problem of finding a Hamiltonian cycle in the graph. Okay? So you want to find a Hamiltonian cycle, but all you know how to do, you want to find a Hamiltonian path, but all you know how to do is to find cycles. Okay? How could you do the reduction? How could you reduce the Hamiltonian path problem to the Hamiltonian cycle problem? Got the Hamiltonian cycle problem solved in your library. Yeah?
If there is a Hamiltonian path and you add, say it's between U and B, and then you add an edge between U and B, now there's a cycle.
Okay, that's almost it. There turns out there's an edge case that prevents that from working.
Okay.
Okay? But let me show you the idea. So here's the schematic for it. Okay? We've got a way to find a Hamiltonian cycle, and somehow we've got to trick it into finding paths for us. That's just explaining what they are. Let me skip ahead. So we want to know if there's a Hamiltonian path here. Okay? That's what we can do. We can take, if we want to know if there's a Hamiltonian path from A to B, we just create a vertex X, add a path from X to A and a path from X to B, then we find out if that thing has a Hamiltonian cycle. Okay? So, if it finds a Hamiltonian cycle, how can we turn that into a Hamiltonian path?
Take X out.
Right. If we find a Hamiltonian cycle, it'll have the edge XB in it and the edge XA in it, right? It has to, because the only way for X to get involved in the cycle is to go through here in some fashion. So if we find a cycle, and we take out these two edges, we're left with a path from A to B. Okay? Now, why wouldn't it work? Instead of doing this, why not do what he suggested? In this case, it would work just to add an edge from A to B and then look for a cycle. But what case might that fail? Yeah?
What if the only path between A and B was just A and B, and then you added a second path?
Well, you'd have to be careful about not adding a second edge. That's true. In this case, there isn't one. What else could go wrong? Okay. How do we know that if we find a cycle, and when we take out the edges XA and XB, that we're going to be left with a path that starts at A and ends at B? How are we guaranteed that here?
Because it passes through X as well.
I mean, the way we've constructed the graph is, whatever the cycle does, it's going to have to go from A to X to B in that order. Or from B to X to A in that order. And so, if we cut this out, those have to be the two endpoints. If instead, we put the edge directly here and found a cycle, that cycle might not go directly from A to B. It might go from B to somewhere, and then to A, and then somewhere. And then there's no way to, we can't take that solution and turn it into a path from A to B. Okay? It may not go directly from A to B. Yeah?
Would that work if we were trying to find Euler paths? Or is it?
Yeah, well, I'd have to think about that. Okay. Anyway, this is just out of time in 30 seconds. This is just our first example of a reduction. We want to solve one problem, namely find a path. We know how to find another problem, which is to find a cycle. So we do a transformation on the graph, find the path, and we find the cycle, and then turn it into a path. That's a reduction.
A reduction is one way. If I gave
Reductions are one way.
So if you gave me an algorithm of finding a Hamiltonian path, you can find a cycle using that algorithm.
No, it would be a different reduction. It may be that if A can be reduced to B, it may be possible to reduce B to A, or it may not. It just depends on the problems.